So this video will be for 15.1, 15.2, and 15.3. So in 15.1, we talk about the properties of water. And one important thing to remember for water is the Lewis dot structure, the Lewis dot diagram. Water looks like this. Okay. So we have those unbonded electrons on the oxygen, and then we have the hydrogen on either end. So let's actually look at what happens when we have multiple water molecules that interact with each other. Because one of the things that you will definitely have to do, maybe not for the quiz, but for the test, is to explain or diagram how hydrogen bonding takes place. So one of the things that's important to keep track of for water is that because we talked about electronegativity a couple chapters ago, which means the ability of an element to attract electrons, oxygen is more electronegative than hydrogen. So oxygen likes to have more electrons around it than the hydrogens do. And as we see in the diagram, oxygen has 8 electrons around it, whereas each of these hydrogens only have 2 electrons. So we actually say that oxygen is, they may use this little S-looking shaped symbol, we say slightly negative. And the reason why we say that the oxygen is slightly negative is because it has more negative electrons around it. Each of these hydrogens are going to be slightly positive. They're further away from those electrons. So if you're farther away from something negative, you're going to be positive. So same thing is true for all of these other water molecules. The oxygens are slightly negative and the hydrogens are slightly positive. So one of the things that actually will happen with water molecules, which can also be used to explain a lot of water's properties, is that we have hydrogen bonding that can take place. So we know that opposite charges attract. So the hydrogen in, let's say, this water molecule can be attracted to that negative oxygen here. This negative oxygen here can be attracted to this positive hydrogen there. And this negative oxygen here, let's say, can be attracted to this positive hydrogen there. So we end up with these hydrogen bonds. And that actually is what keeps water molecules stuck together. And so what will end up happening is because of these hydrogen bonds, the water molecules will be attracted to the water molecule around it, above it, to the side, left or right. So we really have these strong, these would be hydrogen bonds. So a couple of the properties that they talk about in 15.1 are all due to water's strong hydrogen bonds. The 2 properties that they would definitely want you to know for 15.1 is, the first one is water's ability to have surface tension. And water actually has a very high surface tension. Technically all liquids of any type have surface tension, but water has one that's very, very high, just like mercury would also have a very high surface tension. So if we talk about what surface tension means, and we said that most of these explanations can be because of the hydrogen bonds. So what surface tension is, let's say we have a table here, and let's say we drop a little droplet of water. We know that the water actually is going to bead, it's going to form a dome, it's not going to spread out. So again, all liquids have surface tension. Some liquids have more than others, and water has a very high surface tension. So what that means is if we were to drop water on a table, the water would actually bead because those particles, those water particles along the outside of this are going to get pulled down and inward, almost like grabbing something and pulling it down. Because of those strong hydrogen bonds, all of those molecules up here on the surface are not going to be able to spread out. They're going to be pulled inward. Now, something that has very weak bonds or very weak intermolecular forces, it would probably be something like this. You drop it on the table, it'll probably all spread out. Nothing's keeping it stuck together. And so we said that water has very high surface tension because of hydrogen bonds. Okay. The next thing that they would want you to definitely also know is that water has a low vapor pressure. So this is going also back to last unit when you guys talked about vapor pressure. Vapor pressure is that pressure of a gas above a liquid. Another way of thinking about vapor pressure is how easily something can vaporize or evaporate. So water has low vapor pressure also because of the hydrogen bonds. And so what that means is if we have a pot, let's say a closed pot with a lid on it, and we have water here, and it's sitting on a flame, we know that water is not going to evaporate as soon as you put the pot on the flame. It's going to take some time for you to get enough vapor pressure or get enough heat in this liquid for them to evaporate. So low vapor pressure just means this water is not going to easily evaporate. It's going to take time. And we said both of these properties are because of the hydrogen bonds. Because those hydrogen bonds are so strong, it's going to take a lot more time and a lot more heat to break those liquid bonds to get something to evaporate. So low vapor pressure means strong bonds. High surface tension also means strong bonds. You're able to suck everything in and hold everything in nice and tight. The last thing that they want you to know is another property of water is that ice is less dense. And it's less dense than liquid water. And that's actually a special property of water. Most solid forms are going to be more dense than their liquid forms. But ice in particular is actually less dense. And the reason why that is when the liquid particles actually freeze, they spread out. So let's say here is one water molecule, here's another water molecule, here is another one here, here's another one here. When they're liquids, they're all attached by hydrogen bonds. And what we would think would happen is as a solid, these particles get forced closer together. So what would normally happen, so this is the liquid phase, what would normally happen as a solid is those particles would get squished closer together into a smaller space, making them more dense. Still have all those hydrogen bonds. That would be what normally happens. They get squished together and become more dense. What actually happens with ice is they actually spread out even further. So it'd be something like that. And they still would have their hydrogen bonds attaching them. But because it spreads out further, all of this in here is just air or empty space. So it actually makes the ice less dense because you have these air pockets. So imagine if these are my fingers and these are the particles of the liquid. They're kind of sliding past each other, going closer and coming apart. Usually when things form a solid, they come closer together and become more dense. What water actually does is it spreads apart. So all those spaces in between my fingers would just be filled with air, which makes ice less dense, which makes ice less dense so that it can float. So that's 15.1. For 15.2, they want you to understand the process of how we make mixtures. So before we do that, let's actually jump to 15.3 and go over what mixtures are, and then we'll come back to 15.2. So for 15.3, they're talking about mixtures. And so one thing to keep track of is there's two different types of mixtures. We have homogeneous mixtures and we have heterogeneous. Okay. Now homo means the same. These are going to be mixtures that are made up of compounds that are about the same size. So one thing to keep in mind for mixtures are when you take a compound and you add another compound. So you add two compounds together. So like water and sugar, or salt and water, or sand and water. So you're taking two compounds together to make a mixture. Now, if you have two compounds that are relatively the same size and they mix well with each other, you can make a homogeneous mixture. Homogeneous mixtures are also called solutions. Right? So if you hear solutions from here on out, it's a homogeneous mixture where the two compounds mix well together. Hetero means different. These are going to be compounds that are different sizes. They're different sizes and they don't mix well. Okay, and we have two different examples of heterogeneous mixtures. We have colloids and we have suspensions. But both of these are types of heterogeneous mixtures. So if we talk about what each of those are, an example of a colloid would be milk or fog. Okay? And you would like to think that milk is homogeneous, but if we actually let milk sit long enough, it will actually separate out, and you'll see that it's made up of different components or different layers. You'll have the cream, and you'll have the sugar, and you'll have the water kind of all separate out. A suspension, an example of a suspension would be like oil and water. Okay. It's clear that oil and water don't mix. You actually would have a layer of oil and a layer of water. So it's very clear to see what the two compounds were that you added together. Now, one of the things about colloids is colloids are a little tricky. Just like we would think milk is homogeneous, colloids actually look like they're homogeneous. Okay, so they look like homogeneous mixtures, but we actually have a little test that we can do just to be sure whether it's a homogeneous mixture or not. So let's say that you have a container of some unknown fluid. Okay. And you're not sure, it looks like a homogeneous mixture, but you're not sure if it's actually a colloid, because colloids are kind of like homogeneous mixtures in disguise. And you don't have time to let it sit to see if it separates, because if you let it sit for a long period of time and it separates, then you know it's actually a colloid. Homogeneous mixtures, no matter how long you let them sit, will not separate. So you don't have time to let it separate to see if it's a colloid, but you want to see which type you're dealing with. You can actually use something called the Tyndall effect. And the Tyndall effect is a little test that you can use to actually see whether you have a colloid or a homogeneous mixture. And what we do for that is we would take a laser, and you put the laser right up against the side of the glass. Okay, so this is our laser. We put it right up against the side of the glass, and what we're looking to see is if we can see that laser going through the liquid out the other side. If we can see it going through the liquid, so if we can actually see that laser beam going through the liquid out the other side, then that means that we actually have a colloid. So if we see laser, that means you have a colloid. And the reason why we would see the laser with a colloid and not with the solution is that colloids are different size particles. So when that light from the laser hits them, they can scatter the light, so you can see the light going through it. With the solution, they're all the same size, so they're not going to scatter the light. They're all going to scatter the light equally, so you actually would not see the laser going through a homogeneous mixture. You would just see it coming out the other end. So it would look more so something like this, where you'd have all this liquid here, and then all of a sudden on the other end, you would see the laser coming out. So that would be if you have a solution. So if you see the laser, it's a colloid. If you don't see the laser, then that means you actually have a solution. And remember, solutions, we said, is the same. Solutions and homogeneous mixtures are the same thing. The other thing in 15.3 that they want you to be able to do is to order the types of mixtures in terms of the size of their particles. So if we do them as far as let's say from smallest to largest. So the mixture that has the smallest particles are the solutions. Next in line would be the colloids. And then the mixture that has the largest particles are suspensions. So these guys have the smallest particles. Colloids are somewhere in the middle, and then suspensions have the largest particle sizes. So just kind of knowing that. Okay. One interesting thing with colloids is the particles in a colloid exhibit something called Brownian motion. And all that is the particles in a colloid are trying so hard to dissolve each other, and they're trying so hard to mix that they constantly move around each other. And that's the Brownian motion. So it's almost like the liquid is kind of turning or mixing itself. Those particles are moving around itself, trying to get it to mix. Eventually, the particles will lose energy and they won't be able to move around each other, and that's when they actually separate out into layers. But as they're moving around each other, that's why colloids look like solutions, because those particles are moving around and trying to mix, it actually does look like they're mixing, even though they're really not. And so when those particles lose energy, they're going to separate, and then it'll be clear for us to see that it actually is a colloid. Okay? So let's jump back to 15.2. So 15.1 was all about water. 15.3 is all about mixtures and how we can make homogeneous and heterogeneous mixtures. 15.2 is focusing just on homogeneous mixtures. So for chapter 15 and the rest of 16, we're only dealing with homogeneous mixtures. We're not dealing with heterogeneous mixtures anymore. So kind of keep that in mind. The only thing you need to know for heterogeneous mixtures are the two types, which are colloids and suspensions. Okay, so now if we focus on just homogeneous mixtures, we're also going to use the word solutions. So we said homogeneous and solutions are synonymous. We can kind of use those words interchangeably. One important word to know, if you aren't sure what it means already, is aqueous. If they say something is aqueous, that means that water is in it, or water is part of the mixture. Another way of thinking about this too is that if it's aqueous, that means it's dissolved in water. So if you were to be given a description in a question or something that says, let's say, an aqueous solution of sodium chloride. So if we break down what this means, solution, okay, we know that means it's a mixture. And more specifically, we know that means it's a homogeneous mixture, because they use the word solution. Aqueous, that means that water is present. And NaCl, that was actually what's dissolved in the water. So the two compounds that we have in our mixture would be water and NaCl. So that's kind of how we can break down what this sentence means. Now, more specifically, you will need to identify two important terms. And I'll write them here: solute and solvent. The solute, and these are components that make up a mixture. We always have a solute and we always have a solvent anytime we're making a mixture. The solute is what gets dissolved. The solvent is what does the dissolving. Okay. A more simplistic way to think about it, if it's easier, the solute is where you have is the one that you have less of, and the solvent is the one that you have more of. Okay. So if we go back to our sentence that says an aqueous solution of NaCl, water is always the solvent. Anytime you have a mixture and water is in it, water is your solvent. So in this case, water is the solvent. And a lot of times we can call water the universal solvent. And what that means is water is able to dissolve most things. So we say that it's the universal solvent. So water is present, automatically water is the solvent. Water always dissolves other things. We don't really have any instances where water gets dissolved. Now in our case, the NaCl, this would be the solute. This is what gets dissolved in the water. So NaCl is the solute, water is the solvent. Let's say they gave you a different scenario where they said that you were making a mixture or a solution that was made up of, let's say, 10 grams of sucrose and 95 grams of benzene. Even if you have no idea what sucrose is and what benzene is, you can look at the amounts. And so we said the one that you have less of is the solute. So this is the solute. The one that you have more of is the solvent. So the benzene is the solvent. Okay. So another easier way to kind of figure out the solute and the solvent. But in any mixture, we have a solute and we always have a solvent. Now if we were to talk about how water dissolves things, let's draw a water molecule. It's like this. We know water has those slightly negative and slightly positive charges based off of oxygen has more electrons around it, so it's negative. has a negative charge. Hydrogens have fewer electrons, so they take on a more positive charge. Let's say we have it and there is another compound like NaCl. Okay. We know sodium is usually a +1 charge and chlorine is a -1 charge. So even though these guys are connected in an ionic, this is an ionic compound, they do have plus and minus charges. Metals are usually cations or they're positive. Non-metals are usually anions or they're negative. So this is convenient because now we have charges. And so the negative part of the oxygen can be attracted to this sodium, and then this positive hydrogen can be attracted to that chlorine. And literally what water can do is it can attach to these ends and pull those two elements apart and actually break this bond. So what will end up happening is we'll end up with just sodium that's kind of swimming around by itself and chlorine that's kind of swimming around by itself, where they broke that attraction or that bond between them. And so water is able to use the fact that it's polar and it has these charges to attract to other things that have charges and pull them apart. So let's look at, so this is an ionic example. So water can dissolve ionic things. Water also can dissolve polar things. So let's look at what water does when it gets into, interacts with something that's polar. So let's say we have something like ammonia. Similarly, nitrogen has more electrons around it. It's going to be slightly negative. These hydrogens are all slightly positive. So what will happen if we were to mix ammonia and water together is that those opposite charges would attract. So this negative oxygen can be attracted to that positive hydrogen. This positive hydrogen can be attracted to that negative nitrogen. And then water's able to attach and literally pull these guys apart and kind of take off hydrogen one at a time if it needs to. So water uses its charges or its polarity to attach to solutes and pull them apart. So let's actually talk about, and there's a great diagram on page 451 of kind of showing how water molecules actually attach to things or attach to solids and pull them apart to dissolve them. Another important thing to note is electrolytes versus non-electrolytes. But before we actually do that, there's something in chemistry called like dissolves like. So what does that mean? So that means that polar compounds, like water, can dissolve other polar compounds. So things that are similar to you, that are like you can dissolve those things. Polar can dissolve other polar. Non-polar compounds can only dissolve other non-polar compounds. Okay, so one of the reasons why water and oil don't mix is that oil is non-polar and water is polar. So they're two different and because they're so different, they can't actually interact and they can't dissolve each other. Water is able to dissolve other polar things and also ionic compounds because polar and ionic, like we saw in the last two examples, they have plus and minus charges just like water does. So water can attract to those plus and minus charges and help to dissolve it. Non-polar compounds don't have plus or minus charges, so there's nothing for the water to attach to dissolve them. Now you might ask, well, how am I supposed to know what's polar and what's non-polar? Well, one thing to keep in mind, this is going back to that Lewis dot diagram, I believe it's chapter 8 that you guys covered a couple weeks ago. Polar things are not symmetrical. Non-polar things are symmetrical. So if you're given something like H2, well, anytime you're bound to yourself, you're going to be symmetrical. Because if we just had hydrogen with another hydrogen, we could split it right down the middle, it would look the same on both sides. But if we have something like, let's say, HCl, this is going to be polar. So H2 was non-polar because it was symmetrical. This is going to be polar because it's not symmetrical. If we were to draw H and Cl, if we split it down the middle, hydrogen does not look like chlorine. So just go back to remembering polar things are not symmetrical. Non-polar are symmetrical. Okay, so another way of looking at this too is that if this is polar, water would be able to mix with this and dissolve it, but it would not be able to mix with this because water is not nonpolar. Only other nonpolar things would be able to mix with this nonpolar compound. Okay. Now, the other thing we need to talk about for this section are electrolytes. So electrolytes are compounds that when dissolved, they form ions. So when dissolved, they form ions. And ions are things with just plus or minus charges. So if we take an example, if we have NaCl, when we dissolve it in water, it's literally going to break the Na and the Cl apart. So we'll have sodium with the +1 charge kind of swimming around, and we'll have chlorine with the -1. Same thing is true if we were to have, let's say, calcium and oxygen, and that be dissolved in water. If we dissolve calcium oxide in water, we'll have calcium and oxygen kind of floating around. We'll have plus and minus charges. These guys can conduct electricity. So one easy thing to keep in mind with electrolytes is that ionic compounds, and that's where we have a metal and a nonmetal, are electrolytes. Covalent, where we just have nonmetals together, these guys are non-electrolytes. Okay? Another way of thinking about it, as long as you have a metal in the compound, it's going to conduct electricity, because metals conduct electricity. If you don't have metals in the compound, it's not going to conduct electricity. So a couple examples, if we were to take C6H12O6, which is glucose or sugar, it's a type of sugar, and dissolve this in water, it'll dissolve. We know that sugar dissolves, but these particles are not going to break apart from each other to form ions. So this will not form ions. And if it doesn't form ions, things with plus or minus charges, it can't conduct electricity, so therefore this is going to be a non-electrolyte. It still will dissolve in water, but the water won't be able to break apart the C from the H's and the O's. So it will dissolve, but it will still stay stuck together as a group, so it will be a non-electrolyte. The last thing in this section are hydrates. Hydrates are compounds that have water absorbed in them. So it doesn't mean that they're liquids, but they do have water absorbed in them. And the general way that we write electrolytes is we do the first part of the chemical formula, we do this dot, and then we do the second part. Now what goes in the second part is usually water. What goes in this first part is usually an ionic compound. So you might have something like calcium, if I give you the name, calcium hydroxide tetrahydrate. Okay. So if we were to do, this is our ionic portion here, calcium hydroxide, that's going to be CaOH2. Tetrahydrate, that's what we put here. Tetra means 4. We have 4 waters. So that would be the formula for this guy here. If you ever have to calculate the percent of water in a hydrate, I'll give you the kind of formula here. If we have to do the, let's say they say, what is the percent of water in a hydrate? We have to take the total weight of water. So water, we know it weighs about 18 if we add up the hydrogens and the oxygens, but we want the total weight of water. So in this case, for our example, we would have 4 waters that we would put in the numerator, not just 1, because there's 4 waters in this whole group. And then the total weight of the hydrate times 100. So as an example, the total weight of the hydrate would be a calcium, 2 oxygens, 2 hydrogens, and 4 waters. All of this would be that total weight of the hydrate. The weight of the water would just be these 4 waters. So we would do the 4 waters weight over the total weight times 100. And usually for hydrates, depending on how many waters you have, hydrates can be as much as, or the water can account for as much as 80% of the weight of the hydrate. That's not uncommon. Just make sure you do your math right. The last thing that we'll talk about is hydrates are things that have water absorbed in them. And we said that doesn't mean that they're liquids. So if imagine when you wash clothes, it's still, and you take it out of the washer machine, it's still solids, but it may be damp. It may have moisture in it. And that's what a hydrate is. It has absorbed water. So we have things that are hygroscopic. Hygroscopic just means these are compounds that can absorb water. Now, they could absorb a little bit of water or they could absorb a lot of water. But if something absorbs water, whether it's out of the air or wherever, it's called hygroscopic. We also have the term deliquescent. Deliquescent compounds, they absorb so much water that they actually turn into liquids. And they form liquid mixtures. Okay? So what that means is, so something can be hygroscopic, but it can absorb so much water that we actually give it its own name. We say this is deliquescent. An example would be the silicone or silica gel packets. If you ever ordered like a pair of shoes or a laptop or some type of electronics from the internet and have it shipped to your house, they have those little gel silica packets that are in there. And the reason why they put it in the packaging is that in case it's in the warehouse or out on your front step waiting for you to open the door, if there's any moisture in the package, those silica gel packets actually absorb the water so that the shoes don't get damaged or so that the laptop you purchased doesn't get the water inside of the motherboard or anything like that. So the silica gel is an example of something that's hygroscopic. It can absorb water, and if it absorbs enough water, it actually starts to turn into a liquid mixture. And that would definitely not be a good thing if you're, a pair of shoes that you bought. But it takes a lot of liquid to turn it, or it takes a lot of water absorption to turn silica gel into liquids. So as long as your package is not in the middle of a thunderstorm or in a very, very humid place, the silica gel can absorb water and still not destroy the shoes or whatever is in the package. So just to kind of recap, hygroscopic is anything that can absorb water, and a lot of compounds can actually absorb water, and when they do that, they form hydrates. So they can absorb water and still be solids, but if they absorb so much water that they actually turn into liquid mixtures, we say that they're deliquescent compounds. So that actually covers all of 15.1, 15.2, and 15.3 that will be on your quiz. There'll be a separate video for chapter 16, which will involve a lot more calculations and concentration things with solutions.